Great. And we are now live on Facebook. So hello, everybody. I want to personally welcome you to the MedRhythms Videocast series. This is a monthly series we are starting where we'll be talking to world experts in the field of neurology, research, rehabilitation, and music, and discussing all things digital therapeutics, rehabilitation, and music and neuroscience. Each month, we will feature a new expert who will provide valuable insight into these important topics. This show will be hosted by me, Brian Harris, the co-founder and CEO of MedRhythms. And we are a digital therapeutics company focusing at the intersection of neuroscience, technology, and music to build interventions that transform the lives of those living with neurologic injury and disease. If you'd like to learn more about MedRhythms, please visit our website at www.medrhythms.com. I hope that you will find today's episode interesting, meaningful, and compelling, and I believe that you will. And today it's an honor to have and introduce our inaugural guest for this series, Dr. Lou Awad. And Lou Awad is a rehabilitation scientist and physical therapist. Dr. Awad is the founding director of Boston University's Neuromotor Recovery Laboratory, a cross-disciplinary research group that works to develop, study, and translate novel rehabilitation therapies and technologies for people living with walking-related disability, with a focus on stroke. Dr. Awad is associate editor for leading open access journals at the intersection of rehabilitation and technology, including the Journal of Neuroengineering and Rehabilitation and the IEEE Open Journal of Engineering in Medicine and Biology. And Dr. Lou Awad is a member of the Stroke Rehabilitation Scientific Advisory Board for ReWalk Robotics and is the chief clinical advisor to MedRhythms. Welcome, Lou, and it's an honor to have you here with us today.
Thank you, Brian. Glad to be the inaugural guest.
No pressure. And so just to dive in,
we can only go up from here, though, right?
I don't know about that. It's going to be a hard act to follow. But as we get started, Lou, we'd love to learn more about you, your background, and the focus of your lab's research at the Neuromotor Recovery Lab.
Yeah, thank you, Brian. So I'm physically in my home office, but virtually, if you can see behind me, is the Neuromotor Recovery Lab. We've been slowed down due to COVID-19 restrictions, of course, but our team is gearing up as we speak. So I'm a physical therapy faculty member at Sargent College in Boston University, and also director of the Neuromotor Recovery Lab, as Brian described. The Neuromotor Recovery Lab physically is a 1,300 square foot motion analysis space. Our instruments, our tools of our trade are those that allow us to study human movement and how movement goes wrong with neurological disease and injury, and then also how rehab interventions can influence movement. And what you see behind me up there are optical motion capture system, embedded ground reaction force plates. We use various wearable sensors like electromyography sensors or inertial measurement units. We do portable neuroimaging, portable metabolic assessments, and we combine all of those tools with clinical assessments like walking speed, how far a person can walk, their balance abilities, and then also integrate that with knowledge of how well they function in the real world, their participation, how much walking that they do. And we take all of this information, this holistic picture of how a person may present, and then we aim to improve that. We develop rehabilitation technologies, rehabilitation interventions that begin in the lab, and our goal is to translate them, get them out of the lab and into the clinic, into the real world, to ultimately advance the science and art of neurorehabilitation.
That's fantastic, Lou. And it's interesting to hear you talk about the translational research and taking technology from the lab into the community. Why is that important? Why is this type of research in your lab important to be doing this?
Yeah, it's a great question. So there is a saying, I remember learning this when I was in physical therapy school, that it takes 18 years for the latest science to hit clinical practice. What that means is we may know today how to best help someone, but that may not trickle down into real world clinical practice for another 18 years. And that number is, to me, like mind-boggling. I've had people in my family who have had conditions like stroke and Parkinson's disease, and just to think that perhaps they're not getting the latest and best treatments, the best to get them functioning at their optimal version of themselves. I can't. I don't think that's something that we can just sit back on. So our goal here in the NRL is to combine the disciplines needed, ranging from your pure theorists and scientists to engineers who can build really cool tools, to clinicians who can inform the building of those tools, and then launch them into the clinic with our true clinical partners who work and breathe this stuff every single day. And we span that continuum. We have this transdisciplinary team because I think that's what's needed to get these ideas from cool idea to impactful therapy in less than 18 years. Yeah.
Yeah, certainly hoping to speed up that timeline a little bit going forward. And I think with the advancement of technologies like this and the research that you're doing at the lab will absolutely move the needle on that front. Mm-hmm. And your focus at this interesting niche of technology and specifically gait rehabilitation. Now, it may seem sort of obvious to the listeners or people watching in now that walking is important, right? It's important to people's independence, and certainly we deeply understand this at MedRhythms. This is the reason why we exist, is to help people improve. But why is walking important to human beings? Why is walking important to the healthcare system even? So could you tell us a bit more about that?
Yeah, well, related to that, I've heard, and so I work with people post-stroke mostly. I also work with people with Parkinson's disease, multiple sclerosis. And one criticism that I've heard often is, well, why don't you work with a non-ambulatory population? So these people are already able to walk, right? Maybe they don't walk well, but they're able to walk. Why not build tools for people that can't walk at all? And I think that type of binary thinking is, one that is thankfully going away. And the reason why I say that is, so we've evolved. Millions of years of evolution has pushed our human neuromotor system to walk a certain way, right? And we walk with the bipedal gait. And that bipedal gait is very special in the sense that we can walk at a relatively fast pace that's relatively stable and economical. And what I mean by economical is we don't spend a lot of energy to walk the way that we do. But when we have diseases like stroke, for example, maybe early on, there's a loss of ability to walk. But then over time, we know that in the first 2-3 months, there's spontaneous recovery and neuroplasticity, neuroorganization that ultimately leads to a recovery of walking ability. But there's still walking impairment, right? So just because I can walk doesn't mean I walk well. Right? And what we see in people post-stroke particularly is that, yes, they're walking on 2 legs. They can get from point A to point B, but they do it in a way that's very effortful. It takes a lot of energy to move from where they are to where they want to be. And they do it in a way that's also unstable in the sense that they're a high fall risk, and they have to use all sorts of tools to reduce that fall risk, like an ankle foot orthosis that helps keep the ankle or the foot from catching the ground, use canes, walkers, all sorts of tools that prevent them from falling to the ground. And then overall, their speed is quite slow. Right. So when we think about mobility, human mobility, fundamental to that engaging our world is the ability to get out and about. And it's not just get out and about by any means necessary. Our world has been designed for a healthy person in mind, unfortunately. And that's a bit changing in some settings. But if you're walking slow, people will pass you by, might bump into you if you're like in a busy mall, for example. If you're unstable, you might fall over. That's not a good thing that you want to do. If it's effortful to walk, you may not walk long distances. You might choose instead to sit in your car while your partner or someone else runs inside to the store, instead of get out of the car and join them and go for a walk around the store, because it's effortful to walk. So from my perspective, our goal is not just to restore walking. Our goal is to restore function and participation. And we do that by targeting the way we walk, the quality of walking, just as much as it's important to get people going from wheelchair to walk. I think walking is such a wide spectrum, and we want to target and get people to fully recovered.
Yeah, and that's a great perspective there. And as we think about, you mentioned there falls, potentially the impact of walking on falls, on independence to be able to actually walk around in the community. And we certainly know that there's implications, even as you said, it's the world is built for independent people, right? So people who can walk as, quote unquote normal, as much as, we don't like to use that word. And even things like crossing the street, right? So we know that you have to walk at a certain speed in order to get across a pedestrian crossway before the lights turn red. So
Right.
there's actually sort of dangerous implications of people who can't walk with speed and with quality.
And what we actually end up seeing is that their level of physical activity in the real world is so much lower. So we hear 10,000 steps per day. That's our target, right? How many steps per day? I'm sure you know this. I wonder how many people in the audience, how many steps per day do you think people post-stroke would walk? The number might surprise you. Sometimes less than 2,000 steps per day. And some of our research studies, we have folks that clock in at about 1,000 steps per day. Some of us might get 1,000 steps per day just walking around our house in the morning, getting ready for work. Some of us might hit 5,000 steps just walking to work. So think about that level of physical activity, how low it is, and the corresponding changes in health and quality of life that might come from that, right?
And you've mentioned a lot about sort of post-stroke. Is this applicable across different deficits that people might have, things like multiple sclerosis or Parkinson's disease, et cetera?
Yeah, great question. So I'd like to think a lot about the presentation in terms of the impairment to the walking, not being disease specific. So I think about the biomechanics of walking. And what I mean by that is when we walk, for example, we move through different subtasks. We have to support our body weight. We have to propel our body weight. We have to transition from one foot to another. We have to clear the ground. And those are just functions of walking, subtasks of walking. And it doesn't matter if you have a stroke or if you had MS or spinal cord injury and you're ambulatory, traumatic brain injury, you're going to have trouble within those subtasks and across those subtasks. So a lot of our interventions, they consider, of course, that etiology in the sense at a global, at a high level, but in the weeds, they target those subtasks of walking. Can I help a person propel better? Can I help a person support their body weight better? Can I help them clear the ground so they don't trip and fall? And a lot of those interventions end up looking the same across disease states. And the other thing is when we think about gait therapies, their effectiveness is predicated on the nervous system's ability to reorganize in response to the therapy. And we have the same nervous system. It responds in the same way to the same type of stimuli. So we know, for example, we have to practice in a task-specific way. If you want to improve walking, we have to target walking. If you want to improve the ability to sit to stand, we have to work on sit to stand. You have to practice in a task-specific way. And then those tasks have to be done in certain fashion. We have to do them in a way that it's high repetition. We get lots of practice. We have to do them at high intensity. The practice has to be salient. We can't just go through the motions. We have to be engaged in the therapy. And that's true across diagnostic states. So the type of impairment in terms of walking, the subtasks, as well as the type of therapy that we have to employ, there's the same basic building blocks.
Mm.
Yeah.
Very interesting. And we mentioned already a bit about the importance of walking to things like independence, et cetera. But you and I have had the conversations a lot before too about the correlates of walking and sort of how walking speed and these things can be correlated to long-term outcomes and fall risk and independence and community ambulation and even mortality. Can you talk a bit about those correlates of walking speed and walking quality to sort of more secondary outcomes that perhaps we wouldn't think about normally?
Yeah, absolutely. So we know that people who walk fast are healthy.
Mhm.
People who walk slow tend to be not as healthy. And with that comes a number of different buckets that we can consider. One of those is healthcare costs, for example. And that might not be something that comes to mind right away, but we do know that the faster folks, their overall long-term healthcare costs are much less than those that walk slower. And as we get older, people think maybe a natural consequence of aging is getting slower, and that's not true, right? Healthy aging is not getting slower, and our goal is healthy aging. And then, in terms of other relationships that might exist. So one question that lots of folks in the field are interested in answering is, why do we walk slower as we get older? And there's a couple of reasons why that has been thrown out there. One is maybe going slower is safer, right? So if I go If I walk too fast, I don't have the functional resources, the dynamic resources to do it at a fast pace. So I slow down to optimize stability. Well, one of the problems with that is we know that if you walk slow, it costs you more energy per step. So you might be walking, let's say it's true that you walk slower to optimize stability, it comes at a consequence of economy, right? So you might maximize stability at the cost of speed and economy, and overall the net presentation is not that optimal healthy aging that you would need to be, continue your weekend warrior activities, or running around with grandkids, if you have them, for example. Yeah.
Yeah, it's interesting, and we certainly know there newer research showing the correlates, and I guess I say newer research, but over recent years showing the correlates between gait speed and fall risk. We know that gait speed and gait variability are two things that are most linked to falls, which actually people may think that, well, actually going slower is safer, but as you point out, it's actually the correlation is the other way, that the faster that you walk with it, that's related to lowering fall risk. So improving people's walking speed is important, which is just an interesting thing for us to think about. Now on this, as we think about the research that you're doing now, Lou, so we set up a good foundation here about why we do this research and why this is important. What sort of projects are ongoing do you have going now?
Yeah, thank you for giving me an opportunity to share some of the work that we're doing. I'll talk about that all day if we can. One thing about increasing speed, we want to do that in a safe way, right? So one thing that we think about in our lab often is the quality of walking. So it's not just that a person can walk fast or far, but they do it through what we call a physiological strategy. And physiological, just fancy word for meaning it looks closer to what evolution has produced in terms of how bipedal walking looks. So we have a number of projects going on in the lab that leverage both new technologies that we're developing or co-developing with other groups, as well as new treatment approaches, so rehab interventions. So let me talk a little bit the technology. So one of the primary ones that we work with right now is soft robotic exosuit technology. These are garment-like wearable robots. So they're, I use early on in the project, I would describe them as Under Armour with cables embedded in them, right? It's like form-fitting clothing type materials with cables that run through them. And those cables, when they contract, they pull the joint closer together or farther apart, depending on where those cables are located. And what these are designed to do, in contrast to like your Iron Man exoskeletons, like the rigid exoskeletons that you might have seen, well, in the movies, the Iron Man and whatnot, but also like military applications and industrial applications. They're developing these rigid exoskeletons to help lift big objects and carry them far distances without expending a lot of energy. Well, these soft systems, they work in synchrony with a person with impaired mobility. And one thing that I've described in some of our prior work is we think about nature as a barrier. So nature, when we build systems for healthy people, we want to actually beat nature. We want the system to work with the person wearing the system so that they are better than what nature left us. So we are already fast, stable, and economical. We want to make you faster, more economical, and more resistant to perturbations when we're a healthy person wearing some of these augmentative systems. But in a person with a neuromotor impairment or any kind of locomotor impairment, what we actually want to do is not beat nature. We want to restore nature. We want to get you back to what nature provided. And we do that in a very targeted way. So these soft exosuits, they may be worn around the calf. They may be worn around the thigh and help with the knee. They may be worn around the waist and help with the hip. So as we walk, we have a residual force generating ability. The system supplements that residual force generating ability to help restore that physiological movement so that you're walking faster, farther, and more stable, closer to what physiology would demand. So that's one technology. But one thing that we do know is you can't just build technologies and expect clinicians to use them or people to use them. So we use a patient, what we call a patient in the loop or user in the loop approach to developing these technologies. So we don't just build them in the lab and then send them out to the clinic for testing. We bring in clinicians, we bring in patients into the lab so that they are participating in that development process from the very beginning. So in practice, it may look like there's a prototype of a system. We bring in patient one, we test it on patient one. We realize all the things we didn't know. We say, thank you, Mr. Jones, Mrs. Jones. We're going to go back to the drawing board. We fix everything up, then bring in that same patient to make sure it works. If it works in patient one, we test it again and make sure it works twice. Sometimes it works the first time, not the second time. And then if it works on patient one, then we move on to patient two and repeat the same exact process. And you might find, given the heterogeneity or the differences across different patients, what worked for one doesn't work for two. So we're going back to the drawing board. And the goal then now is developing the technology or refining technology so it works for both patient two and patient one. And then we keep repeating that process over and over and over again until we get to a certain number of patients, whatever number that is, depending on the technology. And then we fix the study, the technology for a study. And then we run the protocol, and then we publish a paper, and then we move on to the next technology. And then the other end of the spectrum, we have clinicians involved. Like in our lab, we have a number of physical therapists that are embedded in our teams in a way that if you walk into a session, it would actually be very difficult for you to tell who the physical therapist is from the engineer. And I think that's a cool part of our work in the sense that they might be both interacting with the patient, they might be both looking at the data, maybe from different perspectives, but they're integrating their expertise to really push the technology forward, and a technology that's actually going to be usable and impactful in the real world.
Yeah. Amazing. Yeah, thank you, Lou, for giving that description. And I think it's so important that as we as people who are building these technologies and doing research on these technologies, that the user is always in the loop, right? We must always have those end users or those people that we're endeavoring to serve involved with the process of building the product, so that we build things that are valuable to them. And we can oftentimes, as the builders of the products or the researchers, miss those fine details that are really important to the actual real world application. So I appreciate you hearing that, or hearing you say that. I mean, you've also recently been involved with MedRhythms products as well in some of our early research on our flagship product in chronic stroke. And for those that are listening, MedRhythms is building digital therapeutics, so building products using hardware, sensors, and software that are based upon the neuroscience of music, leveraging decades of a foundation of research on how music, and specifically rhythm, can engage the motor system and can engage the damaged motor system to improve walking outcomes. It's what we call auditory motor entrainment. And specifically looking at a clinical intervention called rhythmic auditory stimulation. And our products at MedRhythms are using the hardware and the software to replicate rhythmic auditory stimulation. So really using rhythm, auditory input to improve motor outcomes. Our flagship product, which Lou has been an important part of and doing some early research on, is in chronic stroke. So we're looking at folks that are at least 6 months post-stroke, and looking at the product's ability to improve walking in that population. And this specific product in chronic stroke was recently granted breakthrough designation by the FDA based upon some of this early research. So could you tell us, about your experience with this? Tell us a little bit about the data that we saw there, Lou.
Yeah, absolutely. So the robotic systems I was describing, their goal was to work in parallel with the user, right, to help move the joints in a way that we think is desirable. What I really love about RAS, the use of rhythm to activate the motor system, is that it's an internal process in the sense that we are leveraging what nature what nature has already provided. We're tapping into that in a salient and meaningful way. When I describe some of our work that we're doing with MedRhythms, I talk about, isn't it awesome that a person can pick a playlist, put on a couple put on headphones, clip on a couple sensors, and walk out the door, and have a therapy that can help them achieve their long-term mobility goals. And so our wearable systems, these robotic systems, they target speed and distance and the quality of motion, and we've seen some pretty fantastic results. And what gets me really excited about something like RAS is we've seen comparable results, if not even better results, than we've seen with some of the other therapies that we've been involved with. And I just described the robotic systems. We've got a lot of other projects going on in the lab. So some of the outcomes we've seen, for example, are improvements in walking speed. We talked a lot about how important speed is. But one thing that we know is that speed is the product of how fast a person moves their limbs, their stepping frequency, or walking frequency, and what their step length is. So both a spatial and temporal contribution to speed. And RAS, if you're doing it on the treadmill, let's say, and it's not specific to MedRhythms, on the treadmill, you can fix the speed, and then you can play a rhythm that's faster or slower. And by playing that rhythm that's faster or slower and asking a person to move to the beat, or they train naturally to the beat, you can modulate their step lengths. Right? By having them walk to different beats, you're fixing the speed, and the step lengths will change. Well, if you put them over ground, it's a much very different result. You play a faster beat, and they'll naturally adopt a faster walking frequency. And because they're over ground and not constrained, they'll tend to walk faster. And with that faster speed, also take deeper steps. And you get this nice synergy between targeting rhythm alone, you get faster walking speeds. But it's not just speed, right? We've also tested changes in their economy, how much effort it requires to walk. And so one thing we know is that there's a concept of limb resonance. Our limbs are built in a way that they move at a certain resonance. It's easier for them to swing at a certain frequency than if they were moving in a different frequency, like a pendulum. Think about a pendulum. And when people have a stroke or have other neuromotor deficits, we end up seeing that their walking frequency is far away from resonance. It's not the frequency that we would expect if we just looked at how long the limb was and computed the resonant frequency just based on that. Whereas in healthy individuals, if I measured your walking frequency, your natural self-selected walking frequency, it would be pretty close to that resonant frequency. So what we end up seeing with something like RAS is they adopt a walking frequency that's closer to limb resonance. So not only are they walking faster, but they're walking with a biophysical profile that's more physiological, what I was talking about before, that term, and thus they're walking with more efficient walking. And we have we just published a paper on the effects on walking speed, and we're working on another paper that looks on the effects of walking economy. And we have some people that are walking 15% more economically. And we're talking about training one session, they're 15% more economical. That's comparable to the effects that we see with these robotic systems that people can also walk and wear. It's comparable to the effect that we see from 12 weeks of rehabilitation training with some other technologies that we've used in the past, like functional electrical stimulation. So it's having a pretty profound effect in both the performance, aka speed, and quality of motion, aka economy. That gets me really excited, I think, about the future of the technology. And then the last part of it, it's music. It's user-preferred music in many cases. It's something that we do daily for recreation. We listen to music, and by pulling that into the therapy session, that increases adherence, it increases enjoyment, it increases outlook and mood, and so many positive effects from just tapping into something as salient as music, but doing it in a very purposeful way, as we are working on right now with MedRhythms. Yeah.
Yeah, thanks, Lou. And I think it's interesting as you hit those points there to think about sort of the functional outcome. And as you mentioned, when we think about using music, and for the viewers at home, RAS, as we use these acronyms, is rhythmic auditory stimulation. So this is the intervention that MedRhythms is replicating and automating with its system. And that when we use music, it's in a purposeful way. It's developing an individualized and challenging therapy, augmenting music to progress people towards functional goals, right? So we're not just saying, hey, listen to Johnny Cash or go listen to Bruno Mars while you walk, and it's going to help you walk better. But in fact, it's really about that purposeful engagement based upon these frequency measures that you're talking about to improve economy and speed.
One of the reasons why it's really important to break down speed into its spatial and temporal contributors, spatial being step length and temporal being walking frequency or cadence, is that we know that healthy individuals, when I try to accelerate and I try to go faster, I use a combination of both a step length and a step frequency. So I both take deeper steps and I take faster steps to go faster. But we see in a lot of these neurological diagnostic groups is that the frequency piece is saturated. What I mean is they tend to rely more on a spatial strategy, taking deeper steps, and there's just a physiological limit. I mean, your legs are only so long. So your ceiling for how fast you can walk is going to be naturally limited unless you can get that walking frequency, that stepping frequency to also catch up a bit. And you have something like music and the rhythm of music doing that. Again, it's a salient way, it's a fun way, it's a cool way to do it, but it's also a biomechanically inspired intervention in the sense that we can drive them to a rhythm that will break through those saturation points that they naturally couldn't achieve on their own. If a person is stuck at 50, 60 beats per minute or steps per minute, and they're not able to go faster than that, but when they're listening to rhythm, they get to 70, 75 steps per minute. That will translate, if you take that and multiply by the distance, their step lengths, that will translate into marked increases in walking speed, substantial increase in walking speed. That's also going to be more economical and also arguably more stable, depending how we define stability. Yeah.
Excellent. And for folks that are interested in learning more about this, as Lou said, this study was just published in Neurorehabilitation and Neurorepair, I guess about 3 weeks ago now, Lou. So almost as close as you can get to saying hot off the press as there is, but you can certainly search that online and find some more specifics about that. I'd love to talk briefly, Lou, a bit more about the metabolic data or walking economy in general. What is walking economy sort of indicative of? How do we measure it, number one, in the research? But then functionally, what does it mean about how somebody walks more economically? What impacts does that have?
Yeah, great question. So when we measure it, at least in our lab-based setting, using a metabolic measurement system, it looks like in practice you either have a mask over your face or a tube in your mouth. And what it does is it measures how much oxygen you end up using. That's actually the output. We look at oxygen utilization. And then what we do know is people with larger body weights versus smaller body weights, they'll just naturally use more oxygen. So we normalize that oxygen uptake by mass, usually divided by kilograms. And then to get walking economy, we further divide that by their walking speed. So our units are at the end of the day, milliliters of oxygen consumed per kilogram of body weight normalized by speed, so by per meter walked. So it's how much oxygen you use per meter walked normalized to your mass. And what uses energy, what uses oxygen is our muscles. Right? At the end of the day, it's those are the things that use energy. Nothing else in our system use energy. And when we say people use more energy to walk, at the end of the day, we're saying they're activating their muscles in a way that requires more oxygen intake. Now, there's two problems to that. You might have a saturation. So there might be a limit. We call that the VO2 max, the oxygen consumption max. And if a person, let's say post-stroke, they have their max over here, call it a number, and they're when they just walk comfortably, their O2 economy is close to that max. They have a very small reserve. And that reduced reserve, what that means is if they needed to accelerate, or they need to walk faster, they couldn't. They don't have much room to go because they don't have enough energy capacity to do so. If they wanted to carry a bag of groceries, they couldn't because carrying a bag of groceries requires more energy and will get them to their physiologic max. And you name an activity that requires more muscle activity, and they're too close to that physiological max. Max, excuse me. So there's that piece there. But then the other thing is, what does that look like in reality? Well, when you see a person walk with intense muscle, with such high muscle activity that their O2 consumption is high, they're not walking normally, right? They're not walking in a smooth, efficient way that we would typically expect. What we end up actually seeing are these very atypical movement strategies. They are lifting their hips up in the air. They're seeing out their leg, a thing called circumduction. They're hip hiking, they're vaulting. They're using so many more muscles and different muscle strategies than we would typically see. So we think about economy as this like holistic measure or this like downstream measure that tells us a lot about how a person moves through space. And there's a saying, wise nature seeks economy of effort. I think that was Giovanni Borelli, the father of modern biomechanics, in one of his books from the 1600s. Wise nature seeks economy of effort. And I'm a pretty, I want to say lazy guy. I have my spurts, right? Where I try not to do things that require so much more energy. I look for an efficient route to doing it. And all these things, the human body wants to do that. We want to optimize energy utilization. We want to minimize energy utilization in activities that we do. So we seek that minimal energy, the strategy that requires minimal energy to do the movement that we're interested in.
Is there potentially an impact here, Lou, as well on endurance, or ability to actually maybe walk farther distances if we are walking more economically?
I think conceptually we can definitely make that link. I'm not familiar with any research that's looked at the link between economy and endurance, but conceptually I think we can think about, well, if it requires more energy to perform an activity, and over time, every single step we take requires more energy, they'll probably have an effect on our performance over time, or our endurance over time. When we think about endurance, one of the clinical measures that we often use to measure endurance is the 6-minute walk test. So the 6-minute walk test is a clinician will instruct the person to walk as far as they safely can in 6 minutes. And that total distance that they can achieve in 6 minutes is highly predictive of their community walking activity. So people that walk farther distances in 6 minutes, they walk more in the community. They achieve more steps per day. And one thing that our lab has recently published on is also their endurance during that test. And what I mean by that is some patients will walk at a certain speed over the 6 minutes. They'll pick a speed and they'll keep that speed over time. And others, they'll pick a speed, but then over time they reduce. They slow down. And we typically expect from a test of endurance is it's challenging enough that you do start at a high level, and over time it's hard to maintain that level. But so we have these endurant people, these individuals that pick a speed and maintain that speed, and non-endurant people that pick a speed and drop over time. Could you take a guess which group performs better in the real world, walks more in the real world? Your endurant people, right? The people who are more endurant. So I think there's a lot to be said about how much energy we're using to move, and the relationship to endurance, and then ultimately our relationship to real world function and quality of life.
Yeah, I'm glad, Lou, that you said that there hasn't been research connecting these two yet, because that leads us into our final couple of questions here for the video cast, which is, where is the future of research going? What is the next round of research? And I'd like to hear your perspective on, where's the future of research for rhythmic auditory stimulation specifically, and where is the future of research, in your opinion, of gait rehabilitation and technology? Where do we go from here?
I think I can answer them both in the same breath, in the sense that I think the future is going to be highly dependent on these multidisciplinary teams that bring together not just the best physical therapists or the best engineers or the best data analytics folks that can do machine learning approaches, but brings them all together under one roof. And they are solving the hard problems. They're bringing their perspectives to the hard problems that so far have limited our ability to practice in the clinic. And I think one of those is the precision medicine one. So it's when we match the intervention to the particular profile or the particular needs of an individual, conceptually we say they're going to have a better time course of rehabilitation. So that precision medicine, right? Precision approach, that's going to require collecting lots of data, big data, data analytics, and ultimately that matching of intervention to impairment. And I think digital therapeutics, they are they can fill that gap in a very meaningful way, especially when we think about the current climate in terms of COVID-19. Less people are coming to the hospital, less people are leaving their homes. Most people are a little bit more averse to seeing their physicians, which, that's not a good thing. If you're not healthy, you should go see your physician. But at the same time, chronic conditions that maybe there is a reason why you might want to delay your next visit, you still should get your therapy. So we're doing a lot of digital or telerehabilitation, telemedicine now. You see almost every discipline, from speech language pathology to physical therapy, occupational therapy, they're doing telerehab services that they never have done before. I know music therapy as well with MedRhythms. And I think this idea of like digital therapeutics, digital technologies that can measure real world movements, that can measure real world ability, bring that back to the clinician to inform the clinical decision making, and then in a very coordinated way, they they can target specific aspects of the things they're measuring. So we measure and treat in the real world in ecological settings. And RAS is one of those things that it's by its nature supposed to be individualized and progressive, right? So this idea that you measure a person's baseline walking rhythm, and then you match the beat to that, and then you progress steadily based on their ability to continue matching that beat. It captures those aspects of individualization and progression that I think really is the future for rehabilitation. And again, does it in a very salient way with music, which is a really cool thing. And I know even the team at MedRhythms, you've got your clinicians, you've got your engineers, you've got users all under the same roof, and you're tackling this hard problem from multiple angles, which is really exciting and really cool to see the future of these technologies.
Well, thank you, Lou, for that. It's great to get your perspective on sort of where we've been, where we are, and where we're going in terms of rehabilitation and gait rehabilitation specifically. And I want to thank you very much for your time and for sharing your amazing expertise and really a very specific niche that you're so good at, but also so versed in. And I appreciate you taking the time to share that with us. And publicly here on Facebook Live with the world. And it's certainly an honor for us to talk with you, but also an honor to have you on our board as well, Lou. So thank you for that. And for everybody else, keep an eye out for our next episode, which will be on December 10th at 4 p.m. Eastern Standard Time with Dr. Michael Tout, who is a leading researcher in rhythmic auditory stimulation specifically, and the founder of neurologic music therapy. So that's sure to be an excellent episode as well. And as a reminder, if you'd like to watch this episode again, we will be posting the recording both on our website and on Facebook page. And if you'd like to learn more about MedRhythms or Lou's lab, please visit our website at www.medrhythms.com. And you can find Lou's lab's information on Facebook, as well as through the Boston University website. So thank you, everybody, for tuning in. Thank you, Lou, again. It was an honor to have you.
Yep. Thank you, Brian. Thank you all.